Welcome to the LemnaTec Academy. In this video, we will look into options for analyzing color in RGB images. In doing so, I will present various options to determine greenness. You may pick the option that fits your definition of greenness best. Let's get into it. Let's start again with our multi-plant example. First, let's create some space in the grid to add the devices we will need later. The simplest option for color analysis is to take the mean red, green, and blue values using the mean color property. Another option is to take the average of the hue, as in HSV or HLS color spaces. We first need to convert the hue using the HSI converter. However, this has two caveats. First, in the output of the converter, the hue angle is represented in a range from 0 to 255, and we need to convert it back to 0 to 360 degrees. We can use the grayscale calculator to do it. First, we have to reduce the number of inputs to 1. Then we open it. The error message is normal in this case. The default formula expects 2 inputs, but we have just 1. We set the formula to A, our first and only input, divided by 256 times 360. We can feed the result into a mean color property. The second caveat is the hue parameter itself. The mean color property just takes the usual average of grayscale values. However, if we want to average the hue correctly, we need to take its periodicity into account. A hue value of 5 represents a slightly yellowish red, and a hue value of 355 is slightly magenta red. However, the standard average is 180, aka cyan. If we take the periodicity into account, the average would be 360 or 0 degrees, meaning pure red. As long as we have only greenish colors and colors closer to green, but no red on the magenta side, this can be ignored. However, it is worth keeping this in mind. In this example, we need to add a writer for each color analysis result, because we cannot add the same extrinsic properties twice to the same object data stream. We need to add here an object's region of interest writer. If we have one writer per color analysis approach, we shall rename the first writer as well. This is a good time to add a remark on best practices for doing this. If you create a new writer, the caption is automatically set to the writer name. With the caption, you add comments to the device, but it can also be used to provide names to reader, writer, and with the configuration maker device. If you rename a writer just by the context menu, then the caption is unchanged. It still shows the old writer name. However, if you clear the caption first and rename the writer then, the name becomes the new caption as well. One note on writer names. These names cannot include any other characters than letters and numbers, with two exceptions. The first exception is underscores. The second are brackets. But brackets can only be added by LemnaGrid itself. All other characters, including brackets, are automatically converted to underscores if you enter them. There's a second option to get the average hue. Use instead of the object region of interest writer, the extended properties writer. And connect it to the RGB average. The mean color property calculates in fact more than the 6 values reported by the normal objects writer. We need the extended properties writer to write them to the database. The mean hue, as reported by the extended properties, has been calculated correctly by the mean color property. Its calculation takes the periodicity of the hue into account, but the output is in the range of 0 to 255 instead of 0 to 360. This has to be fixed by a formula in Lemna experiment. The next option for color analysis, and greenness in particular, is to measure how different a color is from an optimal or ideal version of this color. Let's say, in particular, green. This can be done using the distance from color device. This device calculates the distance between the color of each pixel and an ideal color defined here. We can now enter our ideal green color. I suggest to use LAB and LUV color spaces here, as they are designed to match the human perception. And I suggest to focus on the color axis only and ignore the lightness. The color axes are A and B or U and V. Let's use LUV. Now look for the ideal green color in the image. I think U equals 85 and V equals 170 might be a good choice. We keep using the L2 metric, which is a normal Euclidean metric. The result is now a grayscale image where the blackest pixels are those pixels where the original color is closest to the optimal or ideal color. We see single-digit values at our plants, but values in the range 30 to 40 for the soil. However, the values for the soil are irrelevant, since we will average only the values within the objects. But what if we include L after all? We use a value of 128 or 50% for the lightness of our ideal green. The result looks a lot clearer at first, but it's also obvious that the result is mostly dominated by L. Therefore, I recommend to exclude L from the calculation in most circumstances. We feed this result to the mean color property device. We can check now our results with the mean gray float value tooltip. We get values like 7.53, 7.739, 14.66, 13.85, and 18.07. The advantage of this approach is that you can document it quite easily in publications. You only need to define the color space you are using and the ideal color and write that you take the average differences to this color for any given pixel in the image. The final two options take a different approach. The first is a color classification device. We send the objects and the RGB image to the input ports. In this device, we can define a number of color classes. Each color is defined by a set of reference colors, and each class has its own signal color used in the result image on the right. Each pixel inside the objects is compared against the reference colors. This is done in RGB color space. The color which is close to the pixel's color defines the color class of this pixel. The numeric result will now be how many pixels in each object are of each color class. This is given an absolute pixel count and relative to the size of the object itself. Let's assume we like to have 3 green classes, bright yellowish green, normal green, and dark bluish green, and 1 background class. We need to rename the existing default classes and add 2 more classes. We also change the signal colors. Now we can add colors by picking them on the left image as in the foreground-background segmenter. In order to avoid ambiguities, we need to remove some colors. We can also add colors directly. We can inspect the result in the Color Class Assignment tooltip. We now need a matching writer, which is in this case the object's CC ROI writer. This writer creates two result images. The first is the same as in the object's region of interest writer. Here we can mark objects, region of interest, and so on. The other is the representation of the color classes. The last option is the mixture of two previous techniques. We first convert the RGB image to a grayscale image representing the hue. Then we use the Histogram CC device, a sibling of the color classification device. This device is somewhat similar to the color classification device. However, it creates classes automatically by dividing the selected data range into a number of bins, each creating one class. Here we are about to characterize greens. For reference, red is at a hue of 0 degree and blue at a hue of 240 degree. If we compress this to a range from 0 to 255, we get 0 to 170. So let's consider values between 40 and 130 as greenish and use 16 bits to represent the range. Let's check the results in the tooltip. The classes are labeled automatically CC_000 to CC_015 and no CC for pixels which are not in the data range. The rest is the same as in the color classification device. You see, we have a couple of options to analyze color using LemnaGrid. I'm sure there are more. For instance, you may use the RGB calculator as we used it in the segmentation video and calculate your own index on how colored an object is. From there, you may use the main color property or the histogram CC. Use what I have presented in these videos as an inspiration for your own image analysis. See you in the next video.